Okay, well, this is Dr. Delahousie speaking, talking to my students in dynamics. I had to leave class early today, and so I promised that I would put some example problems on video for you to be able to watch to help you get ready for your homework. And these are a couple of the problems that I would have worked in class if I had been there the entire period. And so the first example that I want to look at is a truck on a slope example. And so reading it, it says we have a pickup truck that weighs 3220 pounds. It reaches a speed of 30 miles per hour from rest at a distance of 200 feet up the 10% incline with constant acceleration. There's a lot of dynamics words in that sentence that we'll have to come back and parse. It says calculate the normal force under each pair of wheels and the friction force under the rear driving wheels. The effective coefficient of friction between the tires and the road is known to be at least a 0.8. Okay, and so this is an example that is certainly going to involve forces coming from the driving wheels of the truck through friction. The truck is traveling in a straight line up this incline. The truck is not rotating, so this is an example of linear motion without rotation. So let's see how we handle this problem. I've placed a picture of the truck and a picture of the free body diagram for the truck here, so we'll keep it in this window in front of us as we move through the problem. And so what we show is, first of all, the 10% slope, or a slope of 1 in 10. We will choose to align our XY coordinate systems. X will align with the slope and Y will align perpendicular to the slope. And on the free body diagram, we will place all of our forces, including gravity, and we'll divide gravity into two pieces, a piece perpendicular to the slope and a piece parallel to the slope heading downhill. W sine of the angle theta and W cosine of theta, where theta comes from the slope of 1 in 10. We'll do the arctangent of that in just a moment. And then we have friction force coming through the tires. We have a normal force in the rear wheel, and we have a normal force in the front wheel. Now, parsing these dynamic words, we are told the weight of the truck. We'll get the mass from that, but here's the key. Reaches a speed of 30 miles an hour, starting at rest, in a distance of 200 feet, with constant acceleration. So that's a constant acceleration problem, meaning we can determine the acceleration since we know the distance traveled, the speed achieved, and the distance traveled. And that is the kind of problem that I would call an ADS equal VDV problem. And we can use the ADS equal VDV form of constant acceleration that says our final velocity is the starting velocity, which is 0, plus 2 times the acceleration of gravity times the distance traveled, using appropriate units, converting 30 miles per hour into feet per second, a distance of 200 feet. From this, we come up with an acceleration of gravity equal to, or the acceleration of the center of gravity of the truck along the x direction of 4.84 feet per second squared. So that was the first little problem hiding in there, is simply find the acceleration. Now we will turn to the free body diagram, which we'll keep up here, and start dealing with forces. Looks like first thing we do, though, is let's go ahead and calculate the slope. Is the inverse tangent of 1 over 10, which is 5.711 degrees. And now from the free body diagram, we'll sum forces in the x direction, and the x direction forces will involve the component of gravity in the x direction, pointing in the negative x direction, and the friction force through the tires pointing in the positive x direction. Those are the only x direction forces we have, so we have friction force positive minus x component of gravity equal mass times the acceleration of gravity. Okay, and the taking this equation and solving it for the unknown friction force, because we know W, we know theta, we know the mass, we know the acceleration of gravity. This is the one equation, one unknown problem, so we can isolate the friction force and solve for a friction force of 804.4 pounds. Okay, so one equation, one unknown here. Then we'll sum forces in, this is mislabeled, this should be the y direction, forgive me. Sum of forces in the y is equal mass times acceleration in the y, but in this case the truck never travels in the y direction, only in the x, so its entire motion is in the y direction is 0, so acceleration in the y is 0. The forces acting in the y direction from the free body diagram would be the normal force in the rear tires, the normal force in the front tires, and the gravitational force. So N1 plus N2 both being shown as positive, minus the weight term is equal to 0. And this is one equation, two unknowns. And then the next thing I'll choose to do is sum moments about the center of gravity of the truck. And we can say that the sum of moments about the center of gravity is I alpha, but alpha, because the truck never rotates, the alpha is equal to 0. And so the moment about the center of gravity would be, since we have the center of gravity 24 high, but left-right, it is centered on the truck, it's going to be 60 times the force at the front, producing a positive moment if we let right-hand rule govern positive, therefore counterclockwise governs positive. Then our friction force also produces a moment about the center of gravity through a distance of 24 inches, and so plus 24 times the friction force, that's also positive. And the rear wheel produces a negative moment about the center of gravity if the other two are positive. So that would be a minus 60 times N2. All of that equal to I alpha, but alpha is equal to 0. Another one equation, two unknowns. We already know the friction force. And so solving this pair of equations, two unknowns, for the two normal forces, we come up with normal force at the front, 1,440 pounds, normal force at the rear, 1,760 pounds, and with this kind of an acceleration up a hill, with this kind of forward acceleration, we would expect a weight transfer from the front wheels to the rear wheels, and this would give us what we would expect. Okay, so this problem is finished. Okay, the second example involves a bottle that is resting on a checkout conveyor at, say, a grocery store. And so the question that we're going to be wondering about is this bottle going to tip over, or is this bottle going to slip? And so let's read the problem statement. It says we have a 2-pound bottle that rests on the checkout conveyor at a grocery store. If the coefficient of static friction is μs equals 0.2, determine the largest acceleration the conveyor can have without causing the bottle to either slip or tip. The center of gravity is located at G as shown in this picture. Okay, and so to solve this problem, again, it fits an object traveling in a straight line. And if we assume that we'll work the problem right up to the moment where it either starts to slip or starts to tip, then still the bottle will not be rotating, and it will have an alpha value of 0 for the bottle, and the bottle will travel on a straight line. So this is the kind of problem where we don't know whether the bottle will first slip or the bottle will first tip. And so to work the problem, we're really just going to have to make a guess, and then we'll have to check our guess and see how things work out. So we're going to work this problem by assuming that tipping occurs before slipping. So we're assuming a smaller acceleration is required for the tipping than for the slipping. And if a bottle is about to tip, here's a configuration of the bottle free body diagram, and it shows certainly there is a normal force from the conveyor belt to the bottle. That normal force would normally be distributed over the bottom of the bottle, but we're assuming that this bottle is about to tip, what I would call impending tip. And if this bottle is about to tip over backwards because of the direction of acceleration shown here, then this bottle will tip over this left corner, and before the tip occurs, the entire normal force will have moved back to this corner. And so we're going to make that assumption. We're going to calculate how much friction force is necessary to cause that to happen, and then we'll see if we have enough friction force for our assumption of tipping first to be true. We could have assumed slipping first, and in either case we'd have to come back and check our answer. Okay, so moving forward and looking at the equations and keeping this picture and free body diagram handy. And we're going to solve the problem two different ways. Probably the conceptually simplest method is first, with our free body diagram, sum the forces in the x direction, and the x direction forces would include only the friction force. Okay, and so we have the friction force acting in the positive x direction is equal to mass times the acceleration of the center of gravity of the bottle, a mass of or a weight of 2 pounds divided by 32.2, and we don't know the friction force and we don't know the acceleration of the center of gravity, so this is a one equation, two unknown problem. Then we'll turn to our other Cartesian coordinate and some forces in the y direction. Looking at the free body diagram, we have the normal force in the y direction labeled positive, and we have the gravity force of 2 pounds acting in the negative y direction. And because the bottle doesn't travel in the y direction, the acceleration in the y direction is 0. And so we'll say our normal force positive minus the weight, which is negative, is equal to mass times acceleration with a 0 acceleration. And this is simple one equation, one unknown. Solving for the value of the normal force is 2 pounds. The final equation that we'll write is we will sum moments about the center of gravity of the bottle. Notice the center of gravity up here at a distance of 8 inches. And we are shown a diameter of the bottle of 1.5 inches, which would make, let's see, sorry, that is the radius of the bottle is 1.5 inches. And so looking at moments about the center of gravity, two forces will cause moments about the center of gravity, the friction force and the normal force. And so we will say that the sum of moments about the center of gravity is equal to I times alpha, but with impending tip, I alpha goes to 0. So our moment, and we'll presume that the friction force produces a right-hand rule positive moment, which it does. We'll call that one positive. So the force acting through a distance of 8 over 12, 8 inches over 12 to convert to feet. Then the normal will produce a moment in the opposite direction, a negative direction. It's the normal force times that distance of 1.5 inch radius, again divided by 12 to convert to feet. So the two moment terms equal to 0 because the bottle doesn't rotate. And then taking, and this is also a one equation, let's see, actually this one is one equation, one unknown, and we can solve for the friction force, 0.375 pounds. Plugging that in here, we can solve for the acceleration of the center of gravity, would be 6.04 feet per second squared. And so if it doesn't slip first, a friction for an acceleration of 6.04 feet per second would cause the bottle to tip. Now the question is, with the normal force that we have, or what friction is available. Okay, the friction available, mu times n, was 0.2 times 2. A friction force of 0.4 must be reached before we slip. But it only takes a friction force of 0.375 pounds to first cause it to tip. So we reach tipping before we exceed the 0.4 friction force, which would cause slipping. So we conclude that we did in fact guess right. If we had guessed wrong, we'd have gone back and recomputed the acceleration and gotten a number lower than this. Now, just to show you an alternative means of determining this acceleration, okay, let's look at a solution method number 2. Solution method number 2 will differ from solution method number 1 in that in solution number 1 we summed moments about the center of gravity, and that included both the normal term and the friction term. Now in this problem, in this solution method, we're going to sum moments about this corner point O. And so we'll use the form of the equation that says when we sum moments about any arbitrary point, that's going to be equal to the moment of inertia about the center of gravity times the angular acceleration of the body, plus a radius vector between the point of interest and the center of gravity, crossed with the mass times the acceleration of center of gravity. And this rho cross ma is in fact the moment of the acceleration about our point O. And so on the left hand side we will have our actual moments, and the only thing causing moments from our free body diagram about point O would be our weight force, acting through a distance of 1.5 inches converted to feet. So a weight of 2 pounds with a moment arm of 1.5 inches converted to feet. That's our only moment about point O, because F and N both pass through point O. So that's our left-hand side. Now what we will do is deal with the kinetic moments, as the author has called them. The kinetic moments for this one would be the I alpha term and the moment of the acceleration of the center of gravity term. Well, in this case, since we are not tipping, the alpha term is 0, but the moment of the acceleration of the center of gravity, and since the acceleration of the center of gravity is horizontal and to the right, that moment is going to be a right-hand rule positive moment, and so we have the mass times acceleration is going to be a mass of 2 over 32.2. The acceleration is unknown, and our moment arm will be a distance of 8 inches divided by 12 to convert to feet. This equation is one equation, one unknown, from which we can directly solve for the acceleration of center of gravity, and we get for that, just as we did in solution 1, a value of 6.04 feet per second squared. Sorry, left that S off. But in this case, it was a one equation, one unknown process to get to the acceleration of the center of gravity, where in the previous solution, it took 3 equations, sum of forces in the X, sum of forces in Y, and sum of moments about the center of gravity to get there. And that ends this second example.